Hello everyone. First, I'd like to thank the organizers for giving me the opportunity to present here a joint work with the rest of the ET modeling team based in Montpellier. Here I present a novel non-Markovian modeling framework used to monitor the epidemic of COVID-19 in France and compare non-pharmaceutical interventions using simulations. The challenge in modeling the COVID-19 epidemics relies on the fact that the contagious period usually starts before the onset of the symptoms. And not all the cases are symptomatic, and only a few are hospitalized. Therefore, a classical compartmental approach requires the introduction of two additional compartments with respect to the simplest SIR model, which are the latent compartment and the asymptomatic infectious period. The problem is that they require the estimation of two transition rates which are difficult to evaluate. What we want to do at the national level is that, given curves of hospital mortality and daily ICU admissions, to reconstruct that of the prevalence curve and as well the reproduction number through time. The challenge is that the hospital data only reflects a delayed and negligible fraction of the dynamics. When considering short-term dynamics, it is usually a problem to make the assumption of exponentially distributed waiting times. For example, if we assume 100 critical cases infected the same day, a classical ODE approach would lead to an exponentially distributed inflow in ICUs. This is not what is observed in the COVID-19 epidemics, where there is a concentration, a peak of patients admitted usually 2 weeks after the contamination. When it comes to anticipate a great inflow in ICUs in order to manage bed occupancy, it is then important to model the transition rates between the different compartments with an aging distribution, such as Weibull distributions. Therefore, the model cannot be Markovian anymore, and it becomes a non-Markovian. That is, it takes into account the age of the infection in its parametrization. The present work is based on an application published online in early April and a preprint available on medRxiv. The model follows the structure starting from a pool of susceptible individuals that can become infected mostly as non-critical cases that will eventually recover, and we assume for the period under investigation that this immunity is full and that there is no immune waning, but a fraction of the infections will lead to critical cases that will require ICU hospitalization or that will die in hospitals. Both kinds of infected people in the general population contribute the same way to the force of the infection, but depending on each one depending on the age of the infection. Within these sequences of progression of the disease, each day has a different contribution according to the serial interval distribution. Mathematically, the model is formalized as follows. We have the susceptible compartment, the non-critical infections, the critical infections, the critical cases, patients admitted in ICU for a long stay, for more than 1 day, that really contribute to ICU bed occupancy, those that will die either after a short stay in ICU or in another ward. The key parameter of this model is lambda I, that captures the dynamics in the general population. The index I reads as the age class. We allow age structure in order to account for age stratified data, in order to parameterize the model for the several waiting times that can differ according to age. For example, the infection fatality rate or the mortality rate in ICU. The time to hospitalization for the critical cases is Y-bill distributed, as well as the serial interval that will be introduced in the next slide. The rho and epsilon distributions, which correspond to waiting time until ICU discharge or death, are exponentially distributed. The model is built in discrete time, therefore it reads as a recurrence relation system, where the second index corresponds to a number of days since the entrance of an individual within a compartment with several days. The force of infection has to follow two constraints. First, because the model is built in discrete time, it has to be bounded by 1. Therefore, it has to converge to 1 if the contact rate and or the prevalence goes to infinity. But at the same time, the law of mass action must be recovered for lower values of contact rate and prevalence. Therefore, the simplest way to account for these constraints is the following expression, where we introduce the R0, the serial interval distribution, the prevalence that is calculated by numerical integration, and the per capita contact rates that can capture the several non-pharmaceutical interventions. The data used to fit and estimate the parameters of the model are those of the weekly average nationwide hospital data, mainly daily ICU admissions, daily mortality, and as well ICU bed occupancy. We have 8 free parameters to estimate, starting from values from the literature, the R0, the initiation day, and the lockdown reduction coefficient mainly. The others are parameters used for fit the distributions of the waiting times, and as well as correction factors, mainly related to fatality rates ratios. The fitting procedure relies on the assumption of a Gaussian noise to minimize therefore leading to maximum likelihood estimates and associated likelihood intervals for the parameters. The quantize of the simulations come from the use of 1000 parameter sets assumed to be equally likely, according to the Wilks theorem. We have shown by right censoring the hospital data that our estimates of basic reproduction number, lockdown reduction effect, and initiation day converge quite early by mid-April to good values, accurate values of that are then conserved till the end of the first wave. Mid-May being the lifting of the lockdown in France. We here estimate that the R0 was about 3 before the lockdown implementation, that reduced by 76% its initial value, and that the first epidemic wave in France started by January 20th. In order to compare our approach to more classical ones that use continuous time ODE and then therefore Markovian memoryless models, we transposed our equations to ODEs and performed the same fitting procedure, and we show here that this classical approach cannot capture the behavior of both curves that are daily ICU admissions and daily hospital mortality. These results suggest that taking into account the age of the infection and more generally memory processes is key to accurately predict the trends in the epidemics in the short term. We can therefore use this framework to, for example, assess the differences in terms of ICU bed occupancy and mortality, in cumulative mortality, depending on the date of lockdown. For example, we have simulate the course of the epidemic with a lockdown implemented 1 week before, and estimated that about 13,000 deaths could have been saved with such an earlier lockdown. Likewise, a later implementation 1 week after of the lockdown would have led to about 52,000 more deaths in hospitals. We have then tried to consider several scenarios while the lockdown lifted. We assume that the reproduction number was greater than 1 in mid-May, just to compare the timings of the second waves depending on the value of the reproduction number or right after the lockdown lifting and the timing of the response. We have shown that above reproduction number of 1.5, there is a massive second wave that is difficult to contain, while a response within 5 weeks for a lower value of reproduction number can reversibly control the epidemic. These results suggest that with values of the reproduction number lower than 1.5, there is time to respond to an epidemic rebound if an adequate NPI non-pharmaceutical intervention is implemented within those 5 weeks, that for greater number reaction within days is required. We then wanted to compare several NPIs using a scale of stringency. We use that of the per capita contact ratio, that is the average potentially infectious contacts an individual has each day relative to the pre-epidemic baseline. We assume there is proportionate mixing, that is the encounter rate at a given time of 2 individuals is proportional to the product of their PCCR. We therefore can construct a relative scale that ranges from the average PCCR during lockdown to 1, that is the pre-epidemic situation, with a threshold value that theoretically corresponds to that of the basic reproduction number equaling to 1. Simulating the course of the epidemic after lockdown lifting till the end of the civil year, using several controls for 3 age groups, before 25, less than 25 years old, between 25 and 65, and above 65 years old, and several control intensity, we show that the cumulative mortality is very well explained by the demographic average PCCR, which means that there is apparently, under the proportion mixing assumption, there is no great leverage of using age differential control to reduce the course of the epidemic. Before analyzing the adaptive control that requires field indicators, I wanted to have the null approach, that is a purely periodic control that alternates lockdown phases with relaxed phases. We show that there is a trade-off that has this graph between the time spent during the relaxed phase and the intensity of the PCCR during this phase. For a fully relaxed phase with no restriction, only less than 20% of the time can be spent during this phase to have the reproduction number less than 1. Finally, we investigated the adaptive control strategy that corresponds to the fact of triggering lockdown once a field indicator value reaches a given threshold, for example daily ICU admissions, and we show that the threshold must have values as low as 15 nationwide patients each day admitted in ICU to prevent consequent increase in the cumulative mortality by the end of the year. But that would lead in that wouldn't perform better than a periodic control. In order to have a longer periods of relaxed phase, we show that we have to maintain restrictions throughout the whole period, for example, to lower the PCCR from 100% to 80%. Future work will consist in exploring more sophisticated NPIs, taking it into account spatialization using metapopulation approaches, and as well allow the values of the key parameters to vary with time. Thank you very much.